the previous lecture, we were discussing about the multi-degree of freedom system with multi-support excitations. We were looking into the equation of motion. The equation of motion can be written in two different forms. One is in terms of the total displacement, that is this equation, in which all the quantities on the left hand side, they are in terms of the total displacement, total acceleration and total velocity. And on the right hand side we have minus Ksg into xg. My Ksg is the coupling matrix between the support degrees of freedom and the ground degrees of freedom, that is the Ksg is the non-support coupling between the non-support degrees of freedom and the support degrees of freedom, that is the degrees of freedom at the ground, and xg is the ground displacement vector. The other form was in terms of relative displacement, that is this equation, in which all the quantities over here are relative quantities, that is relative displacement, relative velocity and relative acceleration. And in this equation we had the R, a matrix called the coefficient matrix, and x double dot g happens to be the ground acceleration vector. The difference between these two equations are that one is written in terms of the total displacement, other is written in terms of the relative displacement. On the right hand side, for this equation we require ground displacement to be specified at each support, whereas here at each support we must know the ground acceleration, and then we can solve the problem. Next we wanted to explain how the R matrix is generated, and in the previous slide that was given, the R matrix is generated with the help of this equation, that is minus KSS inverse into KSG multiplied by xg, or the R matrix is equal to minus KSS inverse into KSG. KSS inverse is the partitioned stiffness matrix corresponding to the non-support degrees of freedom, and KSG is the coupling matrix between the non-support degrees of freedom and the ground degrees of freedom. So, once you are able to get these two matrices, then one can construct the R matrix. So, we had shown an example for this in the previous lecture. This is a frame in which we had three ground excitations at three different supports, and these were the two degrees of freedom which are the non-support degrees of freedom. So, the partition matrix for that, or KSS matrix, was this, the KSG was this, and then with the help of the equation for R, we calculated this quantity, that is KSS inverse KSG, and that turned out to be 1/3 into 111 and 111. So, the three ground displacements share equally in producing the non-support responses at the non-support degrees of freedom. Next we take another example to illustrate the same R matrix, that means how we can construct the R matrix for a pitch roof portal frame. In this pitch roof portal frame we have the 1, 2, 3, these 3 degrees of freedom are the rotational degrees of freedom, and the 4 and 5 they are the translational degrees of freedom. In addition to that, we have 2 support degrees of freedom, that is 6 and 7. So, first what we do, we write down the stiffness matrix for the entire thing, that is for all the 7 degrees of freedom. We write down the stiffness matrix the way we write down the stiffness matrix for a static analysis, and then we partition them. For example, x1, x2, x3, they are the rotations, and these rotations are taken on the top. So, this is the 3 by 3 matrix corresponding to the rotational degrees of freedom, and this is the matrix 3 by 4 that we are calling as KRU. This is the coupling between the rotational degree of freedom and the translational degree of freedom, and this 4 by 4 is the translational degrees of freedom, and the 4 by 4 square matrix correspond to that. So, from this matrix we can obtain a condensed stiffness matrix corresponding to these 4 degrees of freedom that we are calling as k bar uu, and this k bar uu will be equal to k uu, that is this matrix, minus k ug ur KRR inverse multiplied by KRU. So, that is a standard condensation procedure that I think all of you know, and once you do that, we get the condensed stiffness matrix corresponding to the translational degrees of freedom. So, this matrix now is the k bar uu matrix is now of size 4 by 4, and in that the degrees of freedom involved are x4, x5, x6 and x7, and again we partition them over here. So, that these are the this is a matrix corresponding to the non-support degrees of freedom x4 and x5, and this is the matrix corresponding to the support degrees of freedom, and they are the coupling matrices. Now, with this we get the value of R using again the previous formulation, that is R is equal to the minus KSS, or R is equal to minus K US inverse into K bar USG, and these two matrices are given over here. So, with the help of that we get the value of R. So, these quantities are shown here in this slide. This portion, that is your KRR matrix, this is KRU matrix, and then this was the K bar UU matrix, and from there we isolated KUS matrix and KUSG matrix, and after that we obtained the value of R by simply multiplying KUS inverse with KUSG, and this is the 2 by 2 R matrix that is generated. Next we take another problem. It is a model of a cable stayed bridge. In that we have degrees of freedom, as this at the top we have a degree of freedom, here we have a degree of freedom 2, and at the center of the deck we consider another degree of freedom which is in the vertical direction. So, we will try to find out the response of the structure for these 3 degrees of freedom, and the entire equation of motion is written for these non-support degrees of freedom. So, in addition to these degrees of freedom, there are rotations at these points, and we have translations at this support point, this support point, and this support point, and this support point. So, we have in all 4 plus 3, 7 translational degrees of freedom. Out of them 4 degrees of freedom are at the supports, 3 degrees of freedom are the non-support degrees of freedom, that is the translational degrees of freedom as 1, 2 and 3, and the rotations are 8, 9, 10, they are the rotations. So, what we do is the first we write down the entire stiffness matrix, that is the stiffness matrix for the entire system, which is a 10 by 10 matrix. Out of that, the first 7 or 7 by 7 stiffness matrix corresponding to the 7 translational degrees of freedom, they are grouped at the top, and the 3 rotational degrees of freedom are grouped at the lower part of this vector. Then we do this matrix condensation using this relationship and condense the entire stiffness matrix to the translational degrees of freedom x 1 to x 7. Once we get this condensed stiffness matrix, then this condensed stiffness matrix is further partitioned into the non-support degrees of freedom, that is the 3 degrees of freedom which were acting at the 2 at the top of the pylons and 1 at the center of the deck. These are the 3 translational degrees of freedom, and other 4 degrees of freedom are at the 4 supports of the cable supported bridge. Once we partition them, then using this matrix and this matrix we can obtain the value of the R matrix. So, in this way we constructed the R matrix for this problem, and the details of this is given here. That means, element by element we generated the different quantities and then assembled them to this 10 by 10 stiffness matrix, and after that we condensed them to the translational degrees of freedom, and from that we had taken out the 3 by 3 submatrix corresponding to non-support degrees of freedom and obtained the R matrix, and the resulting R matrix was this. So, here again for the 4 different ground motions, we have this 3 by 4 matrix, and with the help of this 3 by 4 matrix we solve the problem. That is the problem in which on the right hand side we have got minus m r x double dot g, where x double dot g are the 4 ground acceleration defined at the 4 support points. Next we see how we can convert these equation of motion that we had written for the multi-degree freedom system with the R coefficient or the R coefficient matrix on the right hand side. In one case in which we are writing down the equation of motion in terms of the relative displacement, and in other case we had the equation of motion in terms of the total displacement, and on the right hand side we had a KSG matrix, and we require instead of ground acceleration, ground displacements. So, those two second order differential equation or multi degree of freedom second order differential equation, they can be written in the state space form as before. Only difference here will be that in the previous case we had for single degree freedom system we had got minus k by m and minus c by m. These were the terms which were written. Now, in place of that, now we have got minus kss into mss inverse. So, this term becomes this. Similarly, the c by m term becomes the css into mss inverse. So, and this one becomes, instead of 1, it becomes I. If we wish to write down the second order differential equation in terms of total displacement as a set of first order differential equation or in terms of the state space formulation, then the A matrix remain the same. Only thing that changes is the F bar 1, and here we see that our F bar becomes equal to minus MSS inverse KSG. This will be not KSS, this will be KSG into XG. So, this will be the only change. Therefore, for multi degree freedom system with multi support excitation, we can write down the equation in 4 different forms. 2 equations can be written as a second order differential equation, one in terms of total displacement and other in terms of the relative displacement, and correspondingly we can have 2 state space formulation for these 2 equations. Now, we try to write down the state space form of the equation motion for the problem 3.4, that is this problem. Yes, for this problem we wish to write down the entire equation of motion in the state space form. So, here we have seen that if we were wanting to write down the equation of motion in terms of your state space form, we have to generate a matrix called A matrix, and that A matrix contains CSS or C by M. So, C matrix must be known. So, that is the first thing that you do for the entire structure. Now, we obtain the C matrix. So, for obtaining the C matrix, this approach is already known to all of you, that one can obtain the C matrix of a particular structure, provided we know the first few frequencies of the system. So, here it was a 2 degree freedom problem, in the sense that there are 2 non support degrees of freedom. So, we had 2 natural frequencies. So, once we know these 2 natural frequencies, then with the help of that one can compute the values of alpha and beta which are required to obtain the C matrix, considering the C matrix to be mass and stiffness proportional. That is, we write down CSS to be is equal to alpha times mass matrix plus beta times the K matrix, and using this we can obtain this damping matrix for the entire system. And once we have these damping matrix written for the system, then we can use the same equation, that is this formulation, that is KSS we know MSS inverse, and also we know now the CSS matrix, and MSS inverse is also known. So, therefore, using this we can write down the entire A matrix, and this A matrix turns out to be like this. Here it will not be 2, it will be 102. You can make this correction, where rho is equal to root over k by m. And on the right hand side, the force vector, if you look at the expression for the force vector, this force vector is equal to minus r into x double dot g. So, r for this problem we obtained as this was the r, that is 1/3 11111. So, using this value of r, one can obtain the value of the f, that is minus 0.33 into x double dot g1 plus x double dot g2 plus x double dot g3. That is what we observed before, that all the three ground accelerations equally influenced the non-support degrees of freedom. So, that is how the terms of the load vector over here that is generated. Now, if we wish to write down the equation of motion in terms of the total displacement and again in the state space form, then the A matrix remains unchanged, as I said before. So, A matrix remains this, and only thing that changes is the right hand side load vector, and the right hand side load vector turns out to be x g1 plus x g2 plus x g3 into rho square, and this is nothing but minus ksg into the MSS inverse. So, ksg into MSS inverse turns out to be this one, and here we can see that the degrees of freedom that we require are not the degrees of freedom, the quantities that is required for defining the force is the 3 displacement at the 3 supports. Now, once we are able to write down the equation of motion in different forms that I described, that is in the state space form and as ordinary differential equation, in terms of relative displacement and in terms of the total displacements, then we come to how we can solve these equations. So, that is what we are calling as the response analysis. Now, the response analysis can be carried out both in time and frequency domain, and first we will take up the single degree of freedom system and the methodology that we will be adopting for solving the single degree of freedom system, that will be extended to multi degree of freedom system later. Now, in time domain analysis, there are many methods which are available. Out of that, we will take up only 2 methods, that is a Duhamel integration and a Newmark's beta method. I think in your dynamics course, all of you have already done these 2 time history methods, which are very popular in earthquake engineering. Therefore, you are acquainted with the different important things associated with these 2 integration strategies. However, we will recast these 2 formulation, that is the Duhamel integration formulation and a Newmark's beta method formulation, in the form of a recursive equations rather than the usual way that you have solved in your dynamics course. Let us take the Duhamel integral first. As you know that a Duhamel integral, we consider the load to be a series of impulses that is the load to be consisting of a series of impulses like this, and these series of impulses, for that if we consider at any time t, we see what is the response that we obtain, and then sum up the effect for, or sum of the responses for all the impulses to get the final response at this particular point. So, what we do is that first we consider a impulse at a time tau from the origin, that is 0 time, and an impulse of f multiplied by d tau is applied to the system or single degree of system at time tau. Then the elapsed time is t minus tau, that is when the impulse is produced over here, then we see its effect at this time, that is after a time of t minus tau. So, that is what we call as the elapsed time of t minus tau. Now, as you all of you know that the problem of producing an impulse to a single degree system is equivalent to producing a velocity to the system or imparting a velocity to the system. So, we can conceive the problem as a damped free oscillation with a initial condition of displacement and a initial condition of velocity. So, in the free vibration equation, if we provide these initial conditions, that is the displacement at, from here we start counting the time. So, at 0 time, if we consider what is the displacement and what is the velocity, then we can substitute this displacement and velocity into the equation that provides you the response at any instant of time t for a damped free oscillating single degree of freedom system. And that is given over here. This is a standard equation, that is the x t minus tau. X t minus tau is the response at time t, and this is given as e to the power minus tau omega n t, and this is the velocity part, that is that if m into x double dot g tau, this is the force, impulse force that is provided at 0 time. So, that is f tau, that divided by m, that becomes the initial velocity, and omega d is the damped frequency. So, and sin omega d t minus tau, d tau comes because f tau d tau, that is the total impulse. So, that is how d tau is coming into picture over here, and this equation is valid for 0 displacement at the initial stage, and a velocity is equal to f tau d tau divided by m. So, for this velocity we get, this is a standard equation for damped free oscillation. Now, this x t minus tau as we obtain, then one can obtain the response x t for all the impulses that acts from this point to a time t. So, we integrate from 0 to t this entire expression over here, and so and this is known as the Duhamel integration, and using this Duhamel integration one can find out the value of the response at any instant of time t. If this f tau is an integrable function, then there is no problem, one can obtain the response of this x t in a closed form analytically. However, if f tau is not a integrable function, then one has to perform a numerical integration for this to get the value of x t. So, instead of doing that numerical integration, one can recast the entire formulation in a slightly different fashion. Let us consider this as the ground acceleration or the support acceleration for a single degree of freedom system, and for that we have a interval of time delta t, so that we can define a time step k and next time step k plus 1, difference between them is delta t. At these two time steps, the values of f k plus 1 and f k, they are known, that is the ground accelerations at these 2 points are known. So, we can multiply them by m to get the forces at these 2 points. Now, if we look at the response at k plus 1, then the response at k plus 1 can be obtained provided we know the response at k, that is the kth time station. And in this kind of formulation, in which we obtain the response at a particular time step with the help of the responses at the previous time step, this formulation is called the time marching formulation. So, in a time marching algorithm, what we do is start with 0 time, and at 0 time the displacement, velocity and acceleration, they are known, and then we obtain the response at the next time step, that is at after the interval of delta t, and then we proceed in this particular fashion. So, this is a time marching scheme, but this time marching scheme to be used in the case of a Duhamel integration requires some kind of consideration, that is what is shown over here in this slide, that what we do is that at k, that is at time t k, we know the forcing function f k. We also know the forcing function at k plus 1 time. Then what we consider, that as if the force between f k and f k plus 1 is varying linearly. That means, it is varying in this particular fashion from this point to this point. And once we assume that that is linearly varying, then at any time tau we can obtain the value of this f tau in terms of f k plus 1 and f k. So, this is what we do here in this formulation, and we write down the f tau in this particular way, and that is, it is a sum of a constant force f k, and then it is a linear term, which is, or the triangular part of the equation. So, using this equation, one can define f tau at any time tau taken or counted from Tk. Now, if we look at the responses at time Tk plus 1, then we see that the response at time Tk plus 1 is consisting of 3 responses. That is, the initial condition that exists at k or the time step k. For that, with that initial condition, the single degree of freedom system vibrates as a damped free oscillator, and because of this vibration there will be some response which will be produced at Tk plus 1, that is the next time step. So, this is the first part of the response. Second part of the response is due to Fk, that is constantly acting over the duration of time delta t, and the third portion is the triangular variation of the load between k and k plus 1. So, the responses for these three would provide the final response at Tk plus 1. So, Tk plus 1 clearly now depend upon these quantities, that is xk, x dot k. So, they are the initial velocity and displacement at kth time step, and Fk and Fk plus 1. So, what we can write down is that xk plus 1 we can write to be is equal to some constant multiplied by Ck xk, some constant multiplied by x dot k, some constant multiplied by Fk, and some constant multiplied by Fk plus 1. Similarly, one can write down x double dot k plus 1 in terms of this equation, where d1, d2, d3, d4 are the constants that is to be obtained. And then one can obtain the value of x double dot k1, that is the acceleration at k plus 1 at time, and that is from the parent single degree of freedom equation. That is, if we know the displacement and velocity of the system, one can find out the acceleration. So, using these three equations, one can get at any time step k plus 1 all the three quantities, that is the displacement, velocity and acceleration in terms of the displacement, velocity at the previous time step, that is k, and the forces which are acting at k and k plus 1, they are eventually known. Therefore, the formulation is centered around finding out this constant C1, C2, C3, C4 and D1, D2, D3, D4. Now, in this we can see that the first part of the solution, that is for the initial condition, this will be a function of xk, x dot k and delta t. Second part of the solution, that is for a constant Fk, that is a rectangular F forcing function. What is the response at this point? So, this will be a function of Fk and delta t, and for the triangular part or for third part of the solution requires the knowledge of Fk, Fk plus 1 and delta t. Now, this comes out, the first solution comes out from the damped free oscillation. In that simply we substitute the initial condition as x k and x dot k, and then find out what will be the response at k plus 1th time step. This one is a problem of a Duhamel integral for a rectangular type of pulse, and for that the analytical solution is available, and all of you have done that. Similarly, for this one the response can be obtained for a triangular kind of pulse, and this also can be obtained using the Duhamel integration because it can be obtained analytically. So, for all the three the analytical solutions are available. Then once we get all the three solutions, then these three solutions are summed up together, and the like terms, that is the terms containing x k, terms containing x dot k, and terms containing f k and f k plus 1, they are all collected together, and the multipliers that will be associated with these variables, they would form the values of C1, C2, C3, C4, etc. And that is what is done over here. And once you are able to find out these quantities, that is C1, D1, C2, D2, C3, D3, etc., then you can write down the equation in this recursive form, where q k plus 1 is equal to a matrix A into q k plus h into f k plus 1, where q basically represents for all the three quantities in a vector form, and A is a matrix consisting of these constants, and the H is again a matrix consisting of sum of the elements of sum of the constants of those equations. So, the C1, C2, C3 etc. can be computed the way I told you, and they are for your information given over here in these equations, and you can see that these C1, C2, C3 etc. depend upon a delta t, that is a time step, and all other quantities are known, that is omega d, omega t, xi, omega n etc. all of them unknown. Therefore, one can compute easily the values of C1, C2, C3, C4, D1, D2, D3, D4 etc. So, that is the recursive form of the Duhamel integration, and it requires the solution of the problem for certain known cases. That is, the known cases are that damped free oscillation, that is a known case, the solution for a rectangular pulse, that also can be obtained using Duhamel integral analytically, and the response for a triangular pulse, that also can be obtained using an analytical solution. So, therefore, with these three known solutions, one can obtain the constant C1, C2, C3, C4 of the A matrix, and one can write down the entire Duhamel integration in this recursive format. The advantage of this solution is that if f tau or the force, if it is not an integrable one, then in any way one has to go for a numerical integration. So, instead of doing that numerical integration, one is using the known solution for a triangular pulse, rectangular pulse, and a damped free oscillation. So, using these three solutions, you are able to tackle the problem. Next is the Newmark's beta method. In the Newmark's beta method, we again solve the problem numerically. using a time marching scheme, that is you try to find out the response at k plus 1 at time step, and with the help of the response at time k, which will be taken as known. So, we start with 0 time t, where all the quantities displacement, velocity and accelerations are specified, and we solve for the next time step using those values, and in that particular fashion we march ahead. Now, the two key equations that are used in the Newmark's beta method are the ones that is shown in this equation 3.52 and 3.53. If we look at these two equations are already known to you. For example, if I ask you to find out the velocity at a particular time given a velocity at some other time t, then you can find out that velocity is equal to the previous velocity plus the acceleration multiplied by the time t. That gives you the velocity x dot k plus 1. Only thing what has been done over here is that the instead of a constant acceleration that we assume over the time interval, here the velocity that is varying or sorry, the acceleration that is varying from k to k plus 1. So, that varying velocity is considered with the help of this particular formulation. That is here we assume that as if the acceleration is varying linearly. Now, if we assume that the acceleration is varying linearly, then it is equivalent to assuming that the displacement is varying quadratically, because if you integrate twice the acceleration, then you get the displacement. So, if there is a linear variation of the acceleration between 2 points, then if the acceleration is integrated, this linear variation will then become a cubic variation, not quadratic, cubic variation. Now, with this assumption, that is the acceleration is varying linearly, then velocity is varying quadratically, and the displacement is varying in the cubic form. With this assumption, we write down this particular two equation, that is given a value of x dot k plus for a given for a given x dot k, we can find out x dot k plus 1 using this particular linear variation of acceleration. Then we can write down from that the displacement at k plus 1 at time step, given the displacement at time step k and velocity at time step k. So, this is again a very familiar equation with all of you. Say if we wish to find out the displacement at a time at some time, then at the previous time whatever is the velocity, that is say u plus v into t plus half f t square. This is what you have all done in your physics class. So, it in fact is a modification of that equation. Here the first two terms remain the same. Here what we have done, we have manipulated the acceleration, that is we are not assuming a constant acceleration and acting between the 2 points, but a acceleration which is varying linearly, and therefore, we take into account the acceleration at both the points and assumed to vary linearly between the 2 points. Now, if we provide the value of delta as half, then this particular term becomes an average acceleration between the 2 points. That is, you can see that it turns out to be x double dot k plus x double dot k plus 1 divided by 2. Similarly, if we consider beta to be is equal to 1/4, then this turns out to be half of the average acceleration into delta t square. Okay. So, we see that for a value of delta is equal to half and beta is equal to 1/4, these two formulations or these two equations provide us the displacement and velocity at k plus 1th station using as assumption that the acceleration is varying linearly, and we assume that the acceleration to be an average acceleration over the time interval. Now, with this assumption we can go ahead in this particular sequence, that is, we write down the equation of motion in the usual form, that is m x double dot k plus 1 c x dot k plus 1 into k x x k plus 1 is equal to minus m x double dot g k plus 1. So, this is the equation of motion at kth time step. We can rewrite it in this fashion by dividing the entire equation by m. So, this is the equation which is written in terms of the frequency and damping. Then what we do is substitute the two equations 3.52 and 3.53 in place of x k plus 1 and x dot k plus 1. So, x k plus 1 and x dot k plus 1, they are now written using equation 3.52 and 3.53 that we have described before, and once we substitute them into the equation, then we can see that the equation that will be there on the left hand side would be in terms of x k, x dot k, x double dot k, and the acceleration x double dot k plus 1. So, the x double dot k plus 1, this acceleration is not known to you or known to us. Therefore, from this equation one can find out x double dot k plus 1, and this will be a function of the known quantities, that is the acceleration, displacement and velocity at the previous time step, and the acceleration ground acceleration at k plus 1 at time station. And once we get the value of x double dot k plus 1, then this can be substituted into the equation 3.52 and 3.53 that I have shown, that is a two cardinal equation. In that equation, if you substitute for x double dot k plus 1, then you get the value of x dot k plus 1 and x k plus 1. So, all the three quantities, that is x k plus 1, x dot k plus 1 and x double dot k plus 1, can be now written in terms of the known quantities of x k, x dot k and x double dot k, and of course, the load. So, this can be written in a compact form like this, that is q k plus 1 is equal to a matrix f n into q k plus h n into f k plus 1. So, f k plus 1 is the load that is acting at the k plus 1 station, and qk is completely known, that is the displacement, velocity and acceleration at k time station, and with the help of that we can obtain the value of the response at k plus 1 time station. Again this is in the recursive form, and this recursive equation provides you the responses, all the 3 responses at a particular time station with the help of the responses at the previous time station. And the Fn matrix and the Hn matrix are given over here. The alpha turns out to be this quantity which can be compensated.